Hello everyone, we're going to take a look at page 7 in your notes packet, and we're going to continue our discussion on using trig identities to simplify, and we're going to introduce also verifying trig expressions. Okay, so let's just start at the top of the page here. We're going to take a look at a simplifying problem, tangent theta plus cotangent theta over tangent theta. Okay, and so there are some tricks we can use to kind of make this problem easier. There are a lot of ways to approach this problem, but I will show you kind of the most streamlined way. Now, if you tried some other techniques that we've discussed and you've seen, those would still work. It would just take you a little bit longer or maybe a few extra steps. Okay, so I'm going to split up this fraction actually right along the middle here at cotangent and tangent, right? So split fraction on top. So note one thing, you cannot do this on the bottom. Okay, so denominators do not ever split up, but numerators can. Okay, so let's see how that's going to turn out. We're going to end up with something like this. Tangent theta over tangent theta plus cotangent theta over tangent theta. And so all I've done is, again, I've kept the denominator the same throughout. It is tangent theta on both of them. Now, this first piece is very simple. Tangent over tangent, yeah, that's just going to be a 1. Okay. Now, what about this second one, cotangent over tangent? Okay. So there are a couple of options. One, we could use sines and cosines, right? We could make cotangent into cosine over sine and tangent into sine over cosine. However, this is one of the rare instances where I will actually use tangent theta is 1 over cotangent theta. Now, the reason that I'm going to do this is because everything that we had was already in terms of tangent and cotangent. So I feel okay doing this. But again, if you weren't sure and you're like, hey, it doesn't seem to be gelling, make it into sines and cosines anyway. Okay. Now, cotangent theta over 1 over cotangent theta, we can flip and multiply this, and we get cotangent over 1. So then we end up with this, plus cotangent squared theta, okay, when we multiply that piece out. Okay, so, look at this. 1 plus cotangent squared, that's one of the identities. This is actually equal to just cosecant squared theta. And that is my simplified answer. Okay, let's take a look at problem B. Now, problem B, again, we're introducing some skills that we learned previously and that we're really going to have to think about to use. Okay, so here is one of the skills that we're going to use. Let's first start by taking this cosine squared and making it into 1 minus sine squared using a Pythagorean identity. Okay, so that identity helped me break this up. Now, you'll notice it looks kind of similar to what's on the bottom. However, the bottom piece is squared. Okay, and so what we're going to do is we're actually going to have to factor this. Okay, and I'm going to use the difference of two squares rules. So if you're not sure, okay, so to factor this, I'm going to pretend like this was just x squared. Okay, so here's 1 minus x squared. And we'll factor this using our a squared minus b squared rule. Okay, so if you think back, you'll remember a squared minus b squared is a plus b times a minus b. Okay, so 1 minus x squared is just going to be 1 minus x and 1 plus x. And the order doesn't really matter for those two. Okay, and let's just think back. We aren't really talking about x's here. We were talking about sines. So we have something like this. 1 minus sine theta times 1 plus sine theta as the factored form of cosine squared, which has been made into 1 minus sine squared. Okay, so if you factor this, this is what we end up with. And then in my denominator, I have this 1 minus sine theta. Okay, so this top part was again just the factored form from 1 minus sine squared. Okay, so hopefully now you've noticed, well, there's 1 minus sine on top and bottom. Let's cancel those out. And I'm just left with this 1 plus sine theta. And this time it didn't simplify to just one piece, but that's about the most I can do with this. So I'm just going to box that off as my answer. So try to keep in mind that you can factor problems if you see something where the pieces are similar on top and bottom, but one side is squared. You can try to factor it and see if one of those pieces will cancel out. Okay. Here's example C. So we've got secant squared minus 1 over secant squared theta. And so what we'll do is the top part is actually a Pythagorean identity. This will just be equal to tangent squared theta. And so now we have tangent squared over secant squared. And now let's turn everything into sines and cosines. Okay, so we've got sine theta over cosine theta, they're both squares, over 1 over cosine squared theta. Okay, keep in mind that since these pieces were squared, we'll keep the entire thing squared as well. Okay, let's do our keep change flip. So sine squared theta over cosine squared theta times cosine squared theta over 1. Let's cancel these guys out. And we're just left with sine squared theta. So this one was pretty straightforward. As long as you thought, hey, let's simplify that top piece first. It has two terms, and you use that Pythagorean identity to make it tangent squared. It's pretty straightforward after that point. Okay, so for example D, I have a lot of different functions here, tangent, cosecant, cosine. So we'll break them down into their fundamental pieces. So tangent, let's make that into sine theta over cosine theta times 1 over sine theta and times, of course, cosine theta. So notice that last piece, I didn't try to change it. It was already something useful to me. And let's just put that cosine over 1. And now we're ready to cancel some pieces out. So I see a sine on top and a sine on bottom. Let's get rid of those. These cosines can cancel out. And I'm actually just left with 1. So that's about as simple as it can get here. Okay, so now let's talk about verifying identities. So verifying is kind of similar to simplifying. However, they're basically telling you what it should simplify into. Your job is just to find what process will transform one side into the other. Okay, so note we generally just start on one side, the more complex side, and we set the other side as our goal. So we take the complex side and we simplify it into the smaller, easier side. Okay, so for example, on example 1, I'm going to say this is the complex side. Okay, and this is the simple side. So I will say that this should be my quote unquote goal. So I'm going to make the left side of this equation become equal to the right side. Let's take a look at how. So let's transform some of these functions. So let's leave sine theta alone. That one's pretty good by itself. Cotangent theta, let's make into cosine theta over sine theta. And how about secant theta? This is 1 over cosine theta. Let's see what we can cancel. And this might seem familiar from the last example, but these sines cancel. We've got some cosines canceling out, and I'm just left with 1. Well, guess what my goal was? That same 1. Okay, so this is an example of verifying where you are showing, hey, I was able to transform these pieces into smaller pieces, cancel stuff out, and it left me with that 1. Okay, let's see how example 2 looks. 1 minus 2 sine squared theta equals 2 cosine squared theta minus 1. Now, this might seem odd because there's squares and there's a times 2, but turning sine into cosine is not hard at all. Okay, so I'm going to just set this side as my goal in this case. And not one side isn't really simpler than the other in this case, but it just happens to be that I'm just going to work from left to right. You could actually start this problem from the opposite side and get the same exact result. Okay, and so Here we go. Let's replace sine squared using our Pythagorean identity with 1 minus cosine squared theta. Okay, and then don't forget to bring the rest of this problem down along with it. Okay, my negative 2 can distribute in here. So I have 1 minus 2 plus, the two negatives cancel each other out, 2 cosine squared theta. Now, you may already have noticed, well, 1 and negative 2 can combine. So I get negative 1 plus 2 cosine squared theta. And if I just rearrange this, this is the exact same thing as my goal side. So really, I only had to plug in one identity to get this to turn into the other side. So as complicated as that one seemed, it was pretty straightforward. Okay, so examples 3, A and B, they relate to factoring, and it's kind of a throwback to what we've done previously. So I will not be solving them here, but refer back to your factoring review as good reference for that material. Okay, so here on page 8, let's verify another identity. Cosecant squared theta minus cosine squared theta, cosecant squared theta equals 1. So where do you guys think we should start? Which side looks more complicated? Hopefully you guys all came up with the same conclusion that this side is complex and the right-hand side is the simple side. So I will use that as my goal. Again, guys, whatever side you set as the goal, the best bet is just don't touch it. Okay? Leave that completely alone and try to get there finally as your final answer. Okay, so there are a couple of ways again to approach this. We can use sines and cosines, we can use Pythag identities. I'm going to again show you kind of the most streamlined one, but there are other approaches to this. So what I noted when I saw this problem was that cosecant squared appears in both of these pieces. And so I'm going to factor this out, okay? So I will take out cosecant squared theta from each piece, okay? And so cosecant squared theta divided by cosecant squared theta is just 1. And then over here, this is going to become just cosine squared theta because I've taken back that cosecant squared out, okay? So 1 minus cosine squared, that one sounds pretty familiar by this point, sine squared theta. And we're multiplying by cosecant squared theta. So cosecant squared theta and sine squared theta, those are actually reciprocals of each other. So I'll just turn this one into 1 over sine squared. Okay. Again, it's always a good idea to make things into sines and cosines. So you can already see what's happening. These sine squareds are going to cancel out. I'm left with just 1. That was my goal all along, and we got there. And finally, we have a few more simplifying questions, so we'll just wrap up with this quickly. Okay, so here I've got sine theta minus cosine theta times sine theta plus cosine theta. And in order to handle this, guys, we're going to again need to distribute this. Okay, and it has that special pattern, the difference of squares pattern. Okay, so you can distribute this out. If you know the shortcut, you can use that as well. But sine times sine will make sine squared theta. We've got plus sine theta cosine theta. Can't really do anything with that. They're just going to stick together when I multiply these two together. Okay. Similarly, when I take the second part here, negative cosine times sine be minus sine theta cosine theta. And finally, my last one, when I take these two, will be minus cosine squared theta. I ran out of room a little bit. Okay. Now, these middle two pieces are the same. They just have opposite signs. So let's go ahead and cancel those. And I'm left with this, sine squared theta minus cosine squared theta. Okay. And they mentioned in the note off to the side here, they said there are actually two ways you can leave this answer. In this case, I'm going to leave it in terms of sine squared, but you could also do it the opposite way in terms of cosine squared. Okay. So what we will do is I'm just going to replace this one because I want to make them at least the same type of function. So let's turn this into 1 minus sine squared theta. Okay. And don't forget this negative. Okay. This negative is very important. Okay. Sine squared theta. So let's distribute our negative sign. It will apply to this whole parentheses. Negative 1 plus sine squared theta. With that sine squared theta in front, let's combine these guys together. 2 sine squared theta plus 1. And that'll be my simplified answer. And it doesn't look super simplified, but it's about the most we can do with this, and so we're going to stop there. Okay, so example B, guys, I'm actually going to suggest that we just skip this example. It doesn't really have a great answer that it simplifies to. The main step that they wanted you to focus on in this example was just distributing, but we've seen how to distribute in a couple of problems previously, so we'll just skip this one for now. Okay, let's take actually a look at problem C, however. This one is the most interesting of the bunch, and that's because this one, it looks like a quadratic. And if you remember, a quadratic is a function based off of x squared. And so what I'll do is I kind of write these in a simpler form so I can factor them, and then I'll rewrite them again with all their trig functions. So I see that this piece is a square. So I'm like, this is x squared minus 2x plus 1. Okay. And I'm going to factor this. So using either grouping or whatever method that you know, you should hopefully find this x minus 1 times x minus 1. Or we could write this as x minus 1 squared. Now, wait a second. Does that even mean? Let's see. This would mean that we're talking about sine theta minus 1 squared. And that's just kind of a nicer way to write the same expression. Okay, so again, in this case, is sine theta minus 1 all squared better than the expression that we had? Maybe. But in some cases, we can use this to help us cancel terms out or maybe rewrite things in lower degrees that will be easier to simplify. Okay, so just keep an eye out for pieces that you can factor. Occasionally, this technique is very useful in breaking these functions down. Okay, so in this case, I would just factor this and I'll say that this is my final answer. And again, the main focus here is just understanding that we can take a expression like this and we can factor it and turn it into something smaller degree and maybe use some of those pieces to cancel stuff out. Okay, so just keep in mind that we can always factor these, even though they may look like they are complicated because they have things like sine squared in them.